First, we're going to look at an excitatory circuit of neurons, where both the first and second neuron in the circuit send excitatory potentials, causing action potentials to be generated. Up top, we have the first neuron, or neuron A. This neuron has already passed an action potential and is now releasing neurotransmitters into the synaptic cleft, or the space between the first and second neurons. These neurotransmitters are glutamate, one of the main excitatory neurotransmitters, and they're represented by these blue dots. The glutamate binds to receptors on neuron B. These receptors are AMPA on the left and NMDA on the right. Both are activated by the binding of the ligand, which is glutamate, and is represented by that blue dot connected to the receptor. This opens the channel, allowing sodium ions and some calcium through NMDA into the cell. The influx of sodium ions creates excitatory postsynaptic potential for neuron B. Neuron B sends the potentials it receives, and if the excitatory potential is large enough, the voltage of the cell will reach threshold and generate an action potential. When threshold is reached, we begin the first stage of an action potential, the rising phase. The voltage-gated sodium channels, represented in purple, open first, and sodium rushes into the cell, where there is a lower concentration of sodium. The positive ions flooding the cell cause depolarization and send the neuron into an overshoot, where the membrane potential briefly turns positive. The voltage-gated potassium channels, represented in blue, are slower to open. When they do open, potassium, which is initially higher in concentration inside the cell, rushes out, resulting in the repolarization of the cell. This is the falling phase. The initial stimulus is the excitatory potential received from neuron A. Then we have the rising phase as the sodium channels open and the overshoot, and the repolarization or the falling phase as the potassium channels open as well. Instead of the signal flowing down the cell like an electric current, depolarization occurs locally down the axon. The depolarization of the previous section of the axon triggers the next portion to open voltage-gated sodium channels. The action potential cannot move backwards on the axon due to the refractory period of the voltage-gated channels. If the axon is myelinated, like in the example seen here, the action potential can jump over the myelinated sections from node to node, where the voltage-gated sodium channels and potassium channels are located. When the action potential reaches the axon terminal, voltage-gated calcium channels open. Calcium is initially higher in concentration outside of the cell, causing it to flood in when the channels open. The calcium ions bind to synaptotagmin, which is a snare protein on the vesicles containing neurotransmitters. This activates membrane fusion, where snare proteins on the vesicles and on the active zone of the axon terminal twist together until the vesicle fuses with the cell membrane and releases neurotransmitters into the synaptic cleft. These are again glutamate neurotransmitters, which will cross the cleft to bind with AMPA and NMDA receptors on the next cell, or cell C. Again, the receptors will open ion channels, allowing the influx of sodium ions. This generates an excitatory postsynaptic potential that will be summed by neuron C and contribute to the membrane potential reaching threshold for this neuron. Excess neurotransmitters are taken up by neuron B and glial cells to be recycled and then terminate the signal. The third neuron will act similarly to neuron B, where it generates an action potential if the excitatory potential is enough to reach threshold. This will again cause the voltage-gated sodium channels and potassium channels to open and generate the action potential.
The second circuit of neurons we'll look at today is an inhibitory circuit. Just like the excitatory circuit, the first and third neurons send excitatory potentials. However, in this circuit, the second neuron sends inhibitory potentials, which prevent action potentials from being generated. Just like in excitatory circuits, glutamate is released from the terminal of neuron A to stimulate an action potential in neuron B. The action potential alters the membrane potential and propagates down the axon via the same mechanisms as in the excitatory circuit. The difference between the two circuits begins in the terminal of neuron B. When the action potential reaches the terminal, depolarization of the membrane causes voltage-gated calcium channels to open, which allows calcium ions to flow into the cell. The calcium binds to synaptotagmin, causing snare proteins on dense core vesicles and the active zones of the axon terminal to twist together. This causes the vesicle to fuse to the cell membrane, allowing the vesicles to release their GABA neurotransmitters into the synaptic cleft. GABA binds to GABA B receptors on neuron C. GABA B receptors are ligand-gated, and once GABA binds to them, they change shape to activate G proteins, which create a cascade, opening chlorine and potassium channels in the cell membrane of neuron C. Negatively charged chlorine flows into the cell, and positively charged potassium flows out of the cell, hyperpolarizing the cell and pushing the membrane potential away from threshold.